Today's topic is factors affecting on stability constant. If we take a metal complex, when metal is coordinating with the ligand, it will result the metal complex. And the equilibrium constant K can said as stability constant K. K is concentration of products and concentration of reactants, right? So this stability constant can be affected by the two factors, that is ligand factors and the metal factors. So first, if we see the ligand factors, basicity of the ligand. What is the basicity of the ligand? The capacity of donating of electrons by the ligand to the metal ion is basicity of the ligand, right? So if the ligand is more basic, it will form strong bond with the metal and the ligand. Therefore, the stability of the metal complex is more and the stability constant K will be high. The next factor is steric effect. If we take the ligand 8-hydroxyquinoline it is. And the second one we see a substituent, that is methyl group. And here the methyl group added at 1, 2, 3, 4th position. It is second position, right? So methyl is a bulky group. When it coordinates near to the donor atom, what will happen? The steric hindrance between the donor atom and the substituent will be takes place. So that the when it coordinates with the metal ion, the bond will be weakened. Therefore, the stability constant will be less. When the substituent is far away from the donor atom, what will happen? It is a plus I group, right? So it donates more electrons to the ligand and the basicity of the ligand will be increases. Therefore, the bond between the ligand and the metal will be strong. Therefore, K is high. That is stability constant is high. If we compare the stability constant values of these three ligands, one is 8-hydroxyquinoline and this one is uh, methyl is substituted second place and here methyl is substituted fourth place. So the third one is having the high stability constant value than the first one and then second, right? So methyl is the bulky group, so mutual revulsion will takes place. Therefore, the bond between metal and the ligand is weak here. And whereas methyl group is far away from the metal ion, therefore here the bond will be strong, therefore K will be high. The next ligand factor is chelate effect. If the ligand is having more than one donor atoms, it can form the ring. For example, ethylene diamine. If it coordinate with the metal ion, so with two donor atoms, it can form the ring like this, right? So this ring can say it as chelate ring. When the metal is having this chelate rings, then the metal complex can say it as chelated metal complex. The stability of chelated complexes are more than that of non-chelated complex. This phenomenon is said to be chelate effect. So if you see, the number of chelate rings increases. For example, here the metal is coordinates with the one ring. Here the metal is coordinated with two rings. Here three rings, right? So here the metal has coordinated with four donor atoms. Therefore, it can form more stable complex. Here metal is coordinated with three donor atoms. So it can form somewhat less stable complex than this one, right? When it comes to one ring, it is coordinated with two donor atoms. So it is less stable complex than the third one, right? So if you see the stability of the complex, if it coordinates with the triene, it will be more stable than the diene, more stable than the monodentate complexes. These two are chelated complexes, where this one is non-chelated complex because metal is coordinating with only one donor atom. The next factor is size of the ring. For example, if the size of the ring is 3 or 4, it can form the unstable complex. If the size of the ring 5 and 6 member rings are stable when they having the aliphatic bonds, non-conjugated bonds. The 6 member rings are stable when they having the conjugate bonds. For example, here acetyl acetone is forming the complex with metal ion like this. Okay, due to pi bond delocalization here, due to the resonance effect, it can form more stable complexes. Next factor is macrocyclic effect. So macrocyclic ring is a large ring, which is having several donor atoms. So it can form, it can coordinate with all donor atoms around the metal ion, right? So it can form high stable complexes. If you see here, it is coordinated with 4 coordinate atoms, 4 donor atoms. Here 6 donor atoms, right? So the stability constant of this complex is 6.1 and the stability complex of this coordinated complex is 2.27. Therefore, the macrocyclic ring will form the more stable complexes. If we see the metal ion factors which are affecting on stability constant of a metal complex. So the metal ion factor is size and charge of the metal ion. Smaller the size, high charge complexes will be forms the more stable metal complexes. For example, if we take beryllium, magnesium, calcium, barium, these are second group elements, right? So by down the group, the size will be increases. So beryllium is having the smaller size than the magnesium, than the calcium, than the barium, so that it will form more stable complexes. Small ionic size of the metal will form the more stable complexes. If we see this complex, the iron is in place 3 oxidation state. Here the iron is in place 2 oxidation state. High charged metal ion will be formed more stable complex. Here cobalt complex also having the high positive charge, so that it is forming the stable metal complex. Next, the electronegativity of the metal ion will form the more stable complex. Electronegativity of the metal ion also plays the role to form the strong metal complexes. So, if the metal is more electronegative, it can have the strong electron attracting tendency. Therefore, it can form the more stable complexes with the ligands. And next, EAN rule. The metal ions which obeys the effective atomic number rule. The metal complexes which obeys the effective atomic number rule will form the more stable complexes. Therefore, K will be high.